Hello, everyone. We are excited to share our project with you, predicting patient survival in heart failure using machine learning. Myself, Vinisha Richala Purushottam, our team, Vashini Sherapur Baswarajappa, Dial Neil, Nagendra Ramasamudra Basavarna, has a deep interest in using technology to address important healthcare issues. So, coming to background, heart failure is when the heart is unable to pump blood as well as it should, which means vital organs and tissues don't get enough blood and oxygen. This leads to symptoms like fatigue, shortness of breath, and swelling in daily life and health. Worldwide, overall, 64 million people suffer from this condition, making it one of the top reasons for hospital visits. Coming to statistics, in the United States alone, around 6.2 million adults are diagnosed with heart failure. It's a significant cause of mortality, with about 13.4% of deaths in 2018 being related to heart failure. Financially, it's a massive burden too. Back in 2012, it's cost the nation about $30.7 billion, including medical expenses. So, our primary objective is to develop a machine learning model that can accurately predict how likely heart failure patients are to survive. By doing this, we hope to assist doctors and healthcare providers in identifying which patients are at higher risk. This will allow for earlier and more precise treatments, ultimately improving patient outcomes. Now that we have an overview of a project and its significance, I will hand it over to Vashini for further explanation.
The dataset used for this present project contains the clinical records of heart failure patients. Each includes various clinical features that are associated with heart failure. The age of the patient, the gender of the patient, whether it is a male or female, the blood pressure of the patient is often recorded as the systolic and diastolic pressures, serum serotonin, a waste product in the blood that comes from the muscle activity indicating kidney function, ejection fraction, the percentage of blood leaving the heart each time it contracts, and the other clinical features such as serum sodium, serotonin, phosphokinase, diabetes, anemia, and the smoking status. Moving to the methodology, we will carry out the different process and the model building of the project. The first model building first process is the data pre-processing, where where we'll be removing the duplicate values and the null values, and we'll make sure that it is optimal data set. And the feature engineering, creating new features and interactions to capture the complex relationship within the data, and implement the model buildings using the machine learning models such as logistic regression, random forest, and the XGBoost to optimize their performance through hyperparameter tuning. And the model evaluation, that is using several metrics such as accuracy, precision, recall, F1 score, and ROC used to ensure the robustness and the reliability. Model stacking, combining the strengths of individual models through stacking or to enhance the overall predictive performance. Data preprocessing, where we'll be handling the missing values of the data set, where we have to do the resampling at a different stages in order to ensure the variable did not get skewed towards the no death event. Handling the outliers, we will be using IQR method, that is interquartile range method, to mitigate the impact of extreme values that can skew the model's learning process. The data normalization normalize numeric features to ensure that they have a similar scale, where we'll be using balancing classes such as mode, which is used to balance the dataset target variable death event. The feature engineering involves of creating a new features from existing ones to enhance the predictive power of the model. Creation of interaction features captures the combine of two or more features. For example, age serum serotonin. This feature is created by multiplying the patient with their serum serotonin levels. It helps to capture how interaction between age and kidney functions affect the heart failure rate. And also the age and the serum sodium interaction between these levels helps to understand how age related changes in sodium levels affect the heart failure outcomes. The polynomial features helps to capture the nonlinear relationship between the feature and the target variable. For example, to generate the polynomial features up to the second degree of the key value, like age, serum serotonin, ejection fractions. This includes the square terms and the interaction terms among these variables. Next slide will be handled by Dylan. Thank you.
Thank you. So when it came to selecting a model, we initially chose three base models. The first was logistic regression, which was a baseline model for the binary classification issue, which provided a straightforward interpretation of the coefficients. We also thought that random forest would be appropriate for this, as it is an ensemble method that builds multiple decision trees and helps merge them together to get more accurate and stable predictions. And then we chose the XGBoost, which is an optimized gradient boosting algorithm, which is good for performance and speed. At the end, we actually ended up stacking the models in order to combine their strengths and enhance the overall predictive performance. When it came to actually building the models, we tuned all their hyperparameters using grid search and cross-validation to find the optimal combination of parameters. The parameters that we chose or tuned for logistic regression were regularization strength, the type of regularization, whether it was L1 or L2, and then the solver, which is the algorithm for optimization. For random forest, we chose the number of trees, the depth of the trees, the minimum samples to split a node, and the minimum samples required to be a leaf node. And for XGBoost, we chose the number of boosting rounds, the depth of the trees, the rate of shrink, the fraction of samples used per tree, and the fraction of features used per tree. And then when it came to the stacking model, we wanted to combine the strengths of all three models by using a meta classifier. So this started with defining the stacking model by using logistic regression, random forest, and XGBoost as base models. And then we used the logistic regression model as the final estimator. From there, we just trained the stacking model on the resampled training data and made our predictions. And then Nagendra will take it from here.
Hi, thank you, Dylan. I'll take from model evolution. The model evolution, it contains a key evaluation matrices. These slides of key evaluation matrices, which are essential for understanding the effectiveness of our predictive models in real world scenarios. Use the accuracy to gauge all over the effectiveness and precision and recall to measure our model ability to identify true causes of heart failure. Currently, the F1 score and the F1 score for the balance between the precision and the recall, the ROC AUC to understand the model and ability to differentiate between the class effectively. These are the model evaluations. I'll next goal would go with result comparison. Yeah, the results across the different models. Our random forest model performed exceptionally well with the highest scores across accuracy, precision, recall, and ROC AUC, demonstrating its robustness in handling complex features interactions. The stack model also showed the strong performance benefiting from the combining strength of individual models. So overall, the result compared to logistic random XGBoost stacking models, the random forest performed outperformed with every other models. I'll say it's the best. Then I'll come to the conclusion. In conclusion, the random forest made clearly performs the best of four models. We attribute this nature of problem. The predicting a heart failure involves identifying complex relationship between features, which RF is good as it's an ensemble of decision trees. While stacking may have given a boost performance, the random forest model generally has strengthened its feature interaction, but reducing variance and the managing clause imbalances may have attributed to its success. But this highlights and the potential assemble the methods of predictive in healthcare applications. This is the conclusion of the project. This is the end, guys. Thank you.